So first off, everyone, welcome to Autodesk Virtual Academy, brought to you all by your friends here at KETIV Technologies. I'm Nigel Mbayak, one of the customer success managers here at KETIV, and the person who happens to jump on these every week with you. So I'm definitely welcome back to those of you who are returning, and welcome to those who this might be your first session. Hope you come back for more in the future. Today, I'm joined by Snigdha here at the KETIV team. Snigdha, how's it going?
Good. How are you, Nigel?
I'm doing great. I'm doing great. And so Snigdha happens to be one of my compatriots on the Ansys division here at KETIV. I'm sure she'll go into kind of what her role is here in a little bit. But if you didn't know already, KETIV is, in addition to being an Autodesk partner, an Ansys partner as well. So we do have technical and sales on both sides, just to provide our customers with the most robust solutions for their needs. So if anyone has any need for some of the software solutions that we talk about today, let us know. I know that Snigdha being on the Ansys team, you might think, like, why, this is Autodesk Virtual Academy. But a lot of what Snigdha is going to be teaching today is general overview and basics with CFD, regardless of what application you're using. So these will apply to the Autodesk CFD products, the Ansys CFD products, so on and so forth. But without further ado, Snigdha, you can go ahead and just introduce yourself to everybody, and we can go ahead and get started.
Sure. Thank you. Thank you. Can you guys hear me okay? Is my voice okay?
Yeah, 100%. Works for me.
Okay. Awesome. Thank you. Thank you, Nigel, for that introduction. Hi, everyone. My name is Snigdha Sarkar. I am the CFD Application Engineer here at KETIV on the Ansys side of things. And I'm going to be presenting some general information about the basics of CFD, and then talk briefly about Ansys software for CFD later on. But hopefully you find some of the content that I present today relevant to your applications, or just, as an introduction to CFD if you're getting started. On the slide here, you see me as being part of the Ansys Application Engineering team at KETIV. We also have John Dow, who specializes in the structures applications, and both of us constitute the application engineering team on the Ansys side of things. Now with that, let's get started. For today's presentation, I will be initially covering the overview of CFD Basics. Now this part should be common and relevant to everybody who's attending, because I'll talk about the basic concepts that are used in computational fluid dynamics. And you can use the same principles, same ideas for any CFD software that you plan to use. And next, I will be talking about Ansys Fluent, basically, how Ansys Fluent comes into the picture, how you can use it for your particular applications, what are the benefits of doing so. And in the end, I'm going to be doing a short demonstration for flow over a cylinder, which is a classic CFD case using Ansys Fluent. Now, keep in mind that the presentation that you're seeing right now, it's been put together at the last minute. So if there are any missteps in me presenting or the content that I share, I apologize at the very beginning. But we're going to have a very general informal discussion over here. If you have any questions, if you have any comments, feel free to put that in the Q&A box on your screens, and I'll definitely get to it towards the end of my presentation. So with that, let me start with the overview of CFD Basics. Now, if you've never used CFD before and you're just, suppose, say, a design engineer or a structures engineer, you might think to yourself, hey, why do I even need CFD? Why do I need computational fluid dynamics? I am designing my products, producing them good enough now. I do the testing when I need to do it, just to verify all the design parameters, and that works fine for me. Now, I'll go over some of the benefits and advantages of using CFD. One of the key important benefits that we see when we use simulation to predict our flow variables is that when you use CFD, you can predict those flow variables over the entire flow domain. You don't have to rely on the measurement that you get from any one particular probe inserted at any one location. And it gets costly as well. When you're doing testing, you have several probes. There's a lot more time, effort, and money that goes into testing it out. So CFD can definitely help you in that regard, wherein doing one simulation will give you values over the entire domain. The second thing is, you have to talk about accuracy at some point. You cannot solve the governing equations of fluid flow analytically, as I'm sure all of you know, right? So that's where CFD comes into the picture, because numerically, you can solve these equations and get whatever values you want for whichever flow variables you're interested in. It could be density, pressure, velocity, anything that is of interest to you, to your application, you can find with the help of your CFD simulation solution. The third thing is, it's definitely less expensive and time consuming, like I mentioned, especially in the case of optimization or, design parameters. Instead of actually building different prototypes with different design parameters, you could rely on your fluid simulation, wherein you could make a small change in your design and see what is the impact on the overall flow very easily using CFD simulations. So again, you get a lot more flexibility, a lot more freedom in coming out with a better product if you rely on simulation. So yeah, with that, I could say that using CFD will definitely help your case if you're not using it already, especially if you're starting off with design engineering. Make sure that you leverage this important capability that Autodesk and Ansys have to offer in order to make your products or processes better. Now, what are some of the important applications where CFD can help you out? It may or may not be relevant to you depending on the application that you're dealing with, but I can say from the Ansys point of view and also from the Autodesk point of view that most of the common CFD applications can be handled by both. You have CFD simulations anywhere where there is some sort of flow in the domain. It could be airflow, it could be lubricant flow, it could be water flow. Anywhere where you have some sort of fluid moving either internally or externally, you can use a CFD simulation if the flow parameters or the flow variables impact the overall efficiency of your product. I have outlined some of the important applications you can see on the screen. If you're using rotating machinery, if you're using any sort of heat exchanger applications, if you're just simply doing pipe losses, right? If you're in the automotive industry and you have to make sure that the engine requirements are met with pressure, etc., with temperatures, etc. Again, CFD can play an important role. You could use it for electronic cooling, chip cooling, any of the multi-phase applications, for example, erosion, cavitation in your rotating machinery. All this can be handled by the commercial CFD software that are available nowadays. So definitely, if you have an application for which you think that CFD could come in handy, but you're not sure, make sure you reach out to us and, we can have a conversation with you and see how CFD fits into the picture for you. Now, I'm talking about CFD a lot. Let's talk about the basics a little bit. How does CFD work? How does the simulation work? What is the software doing behind the scenes in order to predict these flow variables that may be very important to your product development, right? Now, it solves your basic mass and momentum conservation equations numerically. Right, you have your Navier-Stokes equations wherein your momentum is conserved, right? And then you have your continuity equation where your mass flow is conserved. Now, these are the basic conservation equations. If you have energy in your simulation as well, wherein you're looking at temperatures and you're interested in heat transfer, then an energy conservation is also solved within the CFD solver in order to predict these values. What you see over here on the right is a picture of a simple computational grid. This is very similar to what you would see, for your structure side, only the mesh differs a little bit when you're doing fluid flow simulation. What you see here is a domain that has been divided into these smaller units called control volumes, right? Now, each of these control volumes represents an individual cell. The conservation equations that I just mentioned, they are basically solved in each of these cells, right? And for each of that cell, conservation has to be maintained. When you do that, you're able to predict the values at any location in your grid because the equations are being solved at all these node points and all these cell centers, right? These equations cannot be solved analytically, meaning you cannot pick up a pen and a paper and solve this and get an answer to what is your pressure, what is your temperature, what is your velocity. So then how does the solver solve it? It uses algebraic equations that are derived from these partial differential equations to discretize the domain and then get numerical solution for your CFD. The numerical solution is not the exact solution. It differs from the analytical solution because there is some error in it, but that error is so minimal that for all intents and purposes, CFD should give you pretty accurate solutions when you are trying to simulate fluid flow, either internally or externally in the domain. So based on the conservation, the preservation of these quantities and discretizing them to convert them into algebraic equations, you get the values that you need at every cell center. So if you wanted pressure at this location, you would get it. If you wanted pressure at this location, you would get it. If you wanted pressure at this location, you would get it. So that basically covers the fundamentals of how CFD works in the background to give you your simulation results. Now, if you were doing a CFD simulation for the first time, right, how would you get started? What is the workflow that you would follow in order to start from your geometry and then ultimately get your results? Now, the very first point is to define the problem, right? Identify your deliverables. What are you looking for? You have a geometry. You want to understand what is the pressure drop in this pipe, right? That would be one of the CFD deliverables. You want to understand what is the temperature at this location. You want to understand what is the density at this location. So these are some of the deliverables that you will have to chalk out even before you start setting up a CFD simulation. Also understand the accuracy factor and the cost requirements. How accurate do you want your simulation to be? Sometimes you just want directional advice, right? You want to do a CFD simulation, you're making changes to your design, you want to understand how the flow path will change if you make this design. If that is the case, then you're not focused on accuracy so much. However, if you're working on the research side of things and you want to use your CFD simulation to validate your design or perhaps pass a test, then accuracy becomes very important. And in that case, you have to start worrying about the meshing requirements, the computing power that is available to you. So take all these factors into account before you start off with a CFD simulation. The next part is pre-processing, right? You have a geometry available to you. You want to do a simulation on it. In order to prep it for simulation, you will have to look into the geometry to see whether it is closed, whether it is watertight. If not, what do you need to do in order to fix the dirty CAD or fix the geometry? Now, sometimes you may not want to invest so much time in actually going into the geometry and cleaning it up. That's okay. There are options available to you wherein you can wrap a mesh around your geometry in order to fix those holes and fix those errors. But in a standard case, by default, I'm assuming that if you're looking for a very accurate solution, you would want to go in and clean up the geometry. The other thing is meshing. When you're doing pre-processing, meshing the domain so that it gets divided into those individual control volumes that I talked about in the previous slide, that part is important, right? Now, depending on whether or not your flow is internal, external, which areas need more refinement, which areas have more flow gradients, you might want to spend some time on understanding, how do I mesh my domain, right? Which areas are important? Which area am I looking at? Does the mesh need to be fine in this region? So all that comes in the pre-processing part. On the right over here, you can see the pictures wherein I have a simple pipe and I've generated a volume from it. I've extracted a flow volume from it, which is basically the internals of this pipe. Now this would be my flow domain in the solution. I have not included the outside solid body because I am not doing any conjugate heat transfer. Right now, I'm just doing a simple pipe flow simulation wherein I want to see the pressure drop between inlet and outlet. In that case, I do not need the solid domain. So I extract the fluid volume and I generate a mesh wherein I have some boundary layers at the inlet and the outlet, right? So this would be a good example to decide what is important for my CFD simulation. If I wanted to simulate heat transfer from the pipe walls into the flow domain, then I should also include the solid domain in my model, right? So these are some of the considerations that go into defining the problem and the pre-processing stage. The next stage is the solver, of course, depending on which CFD software you're using. You could be using Autodesk CFD, you could be using Ansys CFD. This is the stage where you define the flow conditions and the physics that you want to include in your simulation. Whatever material you want to use, whether it is for the fluid domain or for the solid domain, whatever model you want to use, and by model, I mean, do you want to use a laminar flow or a turbulent flow? Do you want to use a single phase flow or a multi-phase flow? So any of the physics that you want to include, this is the stage where you will set it up. With any fluid problem, you'll always have to define the boundary conditions, the initial conditions, and I guess that is true for structures as well, where you specify the load conditions before doing a simulation, right? And of course, you'll have to select the solver in terms of which discretization method do you want to use in order to solve these equations numerically. Now, most of the commercial CFD software that is available nowadays have predefined settings to give you the best possible, most optimum solution. But in case you're more of a CFD expert and you want to play around with the solver settings yourself, you have the option to do that as well. And lastly, you will figure out the monitors for convergence. And by convergence, I mean that these equations that are being solved, they are not solved in one go. It's an iterative process wherein you keep predicting the answer unless and until the answer does not change anymore. So the stage at which the CFD solution does not change anymore with progressive iterations is the stage where we achieve convergence. You might also want to set up flow monitors. For example, if I had a probe at this location, which was measuring the pressure, and you wanted to compare your CFD results to your experimental results, then you could basically assign a point or a surface here at this location in your CFD to get the pressure for different iterations. This would be a flow monitor. So as soon as the pressure at that flow monitor location stops changing, you would know my solution has converged. So all those things can be done within the solver that you use. And lastly, after the solution reaches convergence, you would want to post-process your results, right? That is the most important part for us because here we're examining results. We are looking at extracting all the deliverables that we initially thought of before starting off with the simulation. If you wanted to use a CFD simulation for marketing purposes, if you wanted to generate cool animations, etc., then even that would be done finally in the post-processing stage. So this basically summarizes the general steps in setting up a CFD simulation and getting it to work for you the way you want. There might be additional steps depending on the complexity of the problem, but for most cases, this should suffice. Now, after this point, I'm going to go into Ansys Fluent briefly because that is the product that I use and have been using for most of my CFD career. Again, I apologize for this not being more Autodesk oriented, but the basic concept of setting up a CFD simulation is quite similar in different CFD softwares and solvers. So if you would just, participate in this AVA and look at the demonstration a little bit, the idea of setting up a CFD simulation should be quite clear to you. You could transfer those same processes and those same steps to any other CFD solver, and that would also work out for you, right? So talking a little bit about Ansys Fluent, this is the primary main CFD software that Ansys has to offer. And I'm going to talk a little bit about the advantages and benefits of using Ansys Fluent and why it is one of the best simulation software available commercially today. Now, one of the things that Ansys Fluent is widely known for is it is one of the most robust and most accurate CFD solutions generator. When I say robust, what do I mean by that? Now, you know that for any CFD solver, they're basically solving equations in the background, right? Now, the accuracy of that solve process depends on a lot of factors, because if you recollect, I mentioned that these solutions are not analytical solutions, they are numerical solutions. So there's always a small degree of error to expect whenever you're doing a CFD simulation. Now that error can be minimized to a great extent, and that depends on how good a solver you're using. Also, how good a mesh you're using. So depending on the meshing elements, the flexibility that Ansys Fluent has to offer, and also the way it couples the different equations in order to derive a CFD simulation, Ansys Fluent is one of the best CFD software out there. It is also well known for solving complex physics. If it is a flow that is quite complex, for example, you're doing a turbulent simulation, you have to take care of resolving the eddies, or maybe you're doing a multi-physics simulation, wherein you have to couple a fluid simulation with a structure simulation. All that can be done in a very seamless fashion using Ansys Fluent, and it gives you the most accurate solution. The other thing, like I mentioned, is multi-physics coupling. You might have to transfer the solution from a fluid simulation to a structure simulation, vice versa. You could also do it between fluid and electronic simulation. All this multi-physics coupling is very well handled by the Ansys environment. On the right here, you see the general workflow of simulations in a platform called Ansys Workbench. It is the general area wherein you couple all your different simulations together. So for example, you see here a structural simulation and a fluent simulation, and see how the solution from the structural and the fluent solution have been fed into a third workflow, which is called system coupling. Now, both these simulations can be handled iteratively, or they could be solved simultaneously. On the right here, you see something, a small, GIF for blade flutter analysis, wherein, you have a blade on which there's some fluid pressure. Now, over time, this might cause your blades to, be degraded, right? So in order to find, good simulation parameters or solutions for this type of analysis, you might want to do a coupled CFD structure simulation, wherein you're mapping fluid pressure on the blade surface and transferring it on to the structure side to calculate the stress. So something of this sort could be easily handled under the Ansys simulation environment. The other thing is the user interface that Ansys Fluent has to offer. You could directly go from CAD import to post-processing all in the same window. You don't even have to step outside the window in order to finish all these steps that I outlined for setting up and completing a CFD simulation. Ansys Fluent has powerful meshing capabilities as well, which is why I say that you can go from CAD import to solving to post-processing. So with the new meshing changes that have been incorporated in the latest, more recent versions of Ansys Fluent, you're guaranteed to get the most optimum, most accurate solution for your CFD. Now, all this sounds a little complicated. What if you're just starting off with CFD and you do not have a lot of knowledge about meshing or about setting up simulations, or you do not have a very good understanding of how, coarse or how fine your mesh needs to be in which region to get the most accurate solution, right? What does Fluent have to offer in that scenario? It has guided meshing workflows for newer engineers that can also be used by experts. Why? Because these guided meshing workflows have outlined very intuitive, very easy to follow steps that you can just keep following from top to bottom. And you will end up having a good quality mesh that one doesn't take a lot of time to compute. And when I say that, I mean that the number of cells or number of, the mesh count is optimum enough. It's not over refining. And the second part is that because the mesh elements, their shape, their skewness, their orthogonality, the quality of the mesh is so good that you don't have to worry about, generating a good mesh. The solver takes care of that for you. It'll auto-generate a mesh that will give you the best possible, most accurate solution, which is what you see on the right over here. This is just an example mesh that was generated for one of the geometries using Ansys Fluent meshing. You can see that the insides of the computational domain, they don't just have any one particular type of cell element, they have different shapes. The interior of the domain has Cartesian grid wherein you have a hex mesh that is very good in terms of orthogonality and maintaining good cell quality. Near the walls where you have high gradients and you want to capture the boundary layer, you have prism cells. And then these prism cells and this inner hex core mesh, they have been blended together with the help of these intermediate polyhedral cells. So this type of meshing capability is only available in Ansys Fluent. It's a patent pending mosaic meshing technology that Ansys Fluent has recently come up with. And what happens when you use this kind of meshing is that the solver automatically decides how to mesh your domain. So you don't have to worry about it. If you're just starting off with CFD, then this would be the way to go in order to generate the best quality meshes, wherein you're relying on the software to do it for you. And gradually over time, you can pick up the theory behind it yourself. So now, I'm going to go into the Ansys Fluent demo. Again, the steps that I follow might be slightly different if you were to use Autodesk CFD. The basic principle, however, the basic idea behind setting something up should be the same, right? And because, again, this was a very impromptu demonstration that, we put together, I'm working with a file in which the solution has already been solved. But I'll go over the settings that I chose in order to set up the simulation. So hopefully it is easy to follow through. So let me go ahead and share that screen. Right. What you see on your screen right now, and do let me know if you cannot see my screen. Nigel, can you see my Fluent screen?
You're good to go.
Okay, awesome. All right. So I'm in the Fluent solver right now. So this is the area where you would set up your CFD simulations. I didn't start with the pre-processing stage because, we can have that conversation for a later date. But if you had a geometry and mesh already prepped, how would you set that up within the Fluent solver is what I'm aiming for. What you see on your screen right now is the mesh for flow over a cylinder. The cylinder is this small circle that you see at the very middle. And because we are not concerned with anything that happens inside the cylinder, the inside of the cylinder is not meshed, right? We generate a mesh around the cylinder body because we are simulating an external flow. So the flow is going over the cylinder and we want to see how it behaves over a standard set of time and how the pressure and the velocity changes. Maybe we can calculate some forces that are acting on the cylinder, the drag and the lift. Now, this is a standard CFD use case that most of the CFD engineers do when they're starting off. This might not be important to your application, but hopefully when I go over the settings, you'll understand the steps that you would have to complete to set something similar for your particular application. Now notice in the mesh is not consistent everywhere. In the areas that are closer to the cylinder, I've chosen a hexahedral mesh. A hexahedral mesh, as in you can see a rectangular grid over here. The reason why I do that, and the reason why the mesh gets finer as it is closer to the walls of the cylinder, is because this is the region wherein I'm expecting most of the gradients to take place, right? At the wall, the fluid velocity is 0. Why? Because at any point, the velocity of the adjacent fluid layer should be the same as the velocity of the solid wall. Since the wall is stationary, the velocity of the fluid is also 0 at this particular point. Now this velocity of course changes as we move away from the wall. Now this change is more drastic near the wall for any particular flow application. So in order to capture those gradients, you will need to have a finer mesh near the wall region for any application that you simulate, right? Especially for viscous flows. Now, as we move away from the wall, we do not care so much about the cell size because we're expecting there not to be a lot of gradients in the far field region. In that region, you could go with the coarser mesh. And the reason you want to go with the coarser mesh is so that you do not increase the number of cells in your domain unnecessarily. If you have a fine mesh everywhere, then your solver has to spend that much extra time to solve those equations at the cell center for all those cells. So we need a good mix of balancing out the cell count and also having a fine enough mesh in the regions of high gradient so that we get an accurate solution. Now this CFD setup that I have over here, flow over a cylinder, this is not to be taken as a guideline for accuracy, because if I were to really look for accuracy, then perhaps I would leave a little more area in the wake region and extend this domain further, because we know that for external flows, capturing the wake region is very important. This is just an example to show you how to set this up. So just use it as a general reference. But if you were to do a more accurate CFD simulation for flow over a cylinder, then do reach out and I can send you some papers that'll tell you about this interesting problem. And I'll tell you why this is interesting as we proceed towards the results section. Now, after going over the graphics, let us look at the other options available to us on this page. Now, in the slides, I mentioned that Ansys Fluent is easy and intuitive to use. What I mean by that is you have certain steps on the left here in the outline view. So if I condense this, you have some basic broad sections for setup, for solution, and then for results, right? Now, when you initially import a CAD geometry or import mesh onto your Fluent solver, you would start off from the very top. And as you keep completing the steps, you would proceed to the solution part. So it's an easy top to bottom approach that anybody can follow and set it up. Now I'm in the general section here. The general section is one of the first steps that you would complete after importing a mesh. Now you have a mesh, you don't know if it's good enough. If you wanted to check the quality, you could do that by reporting the quality. You could also check the scale, you could display the mesh, and you could also change the units, right? So for example, in this case, if I wanted to report the quality of the mesh, I would simply click on this. And on the console here at the bottom, you will see what is the orthogonal quality of the mesh, right? Now, the orthogonal quality of this mesh looks quite good. So we can say that, okay, this is a fine enough mesh that will generate somewhat accurate results for my solution. When I say somewhat accurate, what I mean is that just because the mesh quality is good, it doesn't automatically ensure that you have an accurate solution. Sometimes you might want to refine the mesh further in order to ensure that your solution is not changing. The moment when your solution stops changing, that's when you know that you have the best possible grid to get the best possible solution. Okay. Now in this case, we're just doing a 2D simulation. So I have selected planar. If you wanted to do a 3D simulation, then you wouldn't select planar here, right? Now this is a case in which your solution never really steadies out. So you would choose a transient setting. That means your solution changes with time instead of a steady formulation. You would choose a steady formulation if you expect your flow to eventually steady out, meaning that your variables will not change after a given amount of time. If that is the case, then go for steady. If you're doing more complicated physics, wherein you expect a lot of dynamic behavior over time, then choose transient. So for this case, I'm going to choose transient, and this is a pressure-based solver. I'm not going to go into the technical details of the pressure-based solver over here, but if you're curious, do let us know in the question answer box, and I can send you some material later on. In the case of models, you will see a variety of models that are available to you. Now, most of these are turned off. For example, if I click on multi-phase, it opens up a dialog box wherein I can choose further settings for a multi-phase flow. This is not a multi-phase flow, it's a single airflow, correct? So we are not gonna choose any settings over here, and that is why this shows up as off. If you wanted to simulate a turbulent flow, you could go here and choose a turbulence model. In this case, I've just selected laminar for the purpose of this demonstration, right? Same goes for the other options. So you can, solve acoustics, you can do something to do with structures, you can solve a heat exchanger problem, you could do a discrete phase analysis, you could account for radiation. Everything that you would want to include in your CFD simulation could be done using the Ansys Fluent solver. As far as the materials go, if you click on the materials, it gives you the materials chosen for both the fluid and the solid domain. Now our fluid domain is anywhere where you see the mesh. If I click on it, you can see that, I have chosen an arbitrary fluid that has a density of 1 and a viscosity of 1. The reason why I'm choosing an arbitrary value of density 1 and viscosity 1 is because I wanted to match my results with the experimental results, for a paper that used similar arbitrary properties for the fluid of flow over a domain. So you can neglect this, but the idea is that whatever material you choose, and you have the option to choose many, you could go to the Fluent database, and if you wanted to choose air, you could simply click on air, and that would get populated. You could choose from a range of materials that you want to include in your simulation. We don't have a solid domain in our simulation right now, but by default, you also have solid materials available to you. So if you were to do a coupled simulation, suppose a conjugate heat transfer, and you wanted to account for the thermal conductivity of the material that you use, then again, the solid material would be a good place to set up the material properties that you want to include in your simulation. So I will close the materials panel now. We next go to cell zone conditions. What is a cell zone? Cell zone are the different fluid domains that you specify in your problem. Right now in this flow over a cylinder problem, there's just one fluid domain, but you could have different fluid domains, right? You could have a specific domain in which you want to basically model the rotational domain or the rotational velocity. It could be a moving domain, and then the outside could be stationary. In that case, you would have to differentiate between the different fluid domains. So right now we just have one, so only one shows up. If I click on fluid over here, you will notice that the material name is set to be fluid, which I just showed you under the materials panel. So the density of one and viscosity of one, that material has been used in this particular flow domain. There is no solid domain in my simulation, hence we only see fluid. If you had solid domain, then that would also be visible. So this is where you would set up the cell zone conditions. Next, we go to the boundary conditions. So the cell zone is for volume and boundary is for surfaces, right? So I have an inlet over here where you can see the blue arrows, and the outlet over here where you can see the red arrows. If you just wanted to display the inlet, you could go ahead and right click on it and choose display, and it'll just show you that one line which you are assigning as an inlet. This is a 2D simulation, so it shows up as a line. If it were a 3D simulation, then it would show up as a surface. So if I click on inlet again, you notice that, I have basically assigned this a velocity of 64 meters per second in the X direction. So you could choose the components, or you could assign a general velocity magnitude. And in this case, I have chosen an arbitrary value. If you look at the outlet, I have set it up as a pressure outlet. So let me go ahead and add this to the graphics window. When I do that, you see the outlet also being visible. So if I click on it, this has been assigned as a pressure outlet with a 0 gauge pressure. If you wanted to change the boundary condition, then you could simply right click on it, go to type, and then you have a host of options. So for example, you don't know the pressure at the outlet, but you know the mass flow at the outlet. How would you assign it? You would simply go and choose mass flow outlet and then enter the value, and that would take care of it. So depending on the boundary conditions that you have available to you, either through test or through general knowledge, you can change the type of boundaries that you set in your simulation to get the most accurate result. When you import the mesh, the wall boundaries get automatically pulled in. So the cylinder wall is the only wall in my domain. And you will see that it's a stationary wall wherein you have the no slip condition. What is the no slip condition? It's simply stating that at the stationary wall surface, the velocity of fluid is 0, which is why there is no slip between the fluid and the solid domains. So I'm just going to go ahead and close it. It's a simple simulation. There's nothing else to be set here. What I have done over here, however, is selected some of these report definitions. Now I mentioned that there might be important values that you're interested in. If you want to monitor those values throughout your simulation, you can simply set up a report definition, and it gets the value of that report definition gets reported out here in the console as your simulation progresses. So if I wanted to calculate the drag, I could just go ahead and do that. I calculate the drag on the wall of the cylinder, and the drag force or the drag coefficient can be directly chosen from the Fluent solver setup. You give it the direction and give it an arbitrary name, and that's how you would get it. I think this part already has a solution, so let me go ahead and compute it. So you can see that the moment I say compute, it gives me the drag coefficient on the cylinder. So this could be one of the values that you're interested in. I did the same thing for lift as well. And once I do that, I'm simply gonna run the calculation. The methods of calculation, which basically means the solver setup that I choose, are default settings in Fluent. Because I'm doing a simple simulation, I don't think it's very complicated. Let me just stick with the default values over here as a CFD beginner. If, for example, your simulation is not converging, if there is some issue with the results, then you might want to come and play around with it. And there is comprehensive documentation available on the Ansys side of things to guide you for this setup. But I'll go ahead and run my calculations. I've already done that behind the scenes. So let's go and look at some of the results. Suppose my simulation has converged and the residuals are not changing anymore. That means that with progressive iteration, I see the same sort of solution. Then I know that my simulation has converged. I'm going to stop it. I have the results, but how do I use it to my advantage? So I basically go to the results section, and you have different options available to you when it comes to results. Now notice that I'm doing all of this in the same user interface. I don't have to step outside of Fluent to get my basic post-processing results. I've already set up a pressure contour here. So you can see once the simulation is complete, I get beautiful contours that I can repurpose for either marketing or use it as a guide to compare my solution to a physical test solution. What I have here is static pressure at the interior domain, and it gives you the scale and the coloring depending on the values that you get from the Convert CFD solution. I did the same thing for velocity as well. So you can see the wake region behind the cylinder very clearly shown in this simulation. Now this is a transient solution. So of course you don't want to look at just one particular time step. You would want to look at it over a period of time. So in order to do that, you could set up an animation wherein you gather the solution from each time and then put that together to see how your solution is varying. So you can do that within Fluent as well, but I did that in another post-processing software that Ansys has to offer, simply because it's a little bit more clearer over here, where you could go to animation and collect all the time steps at which you have available solution, and then just simply click the play button to see how the simulation progresses. I would do that here, but it takes a lot of time. I don't know if it is transferring dynamically over to the presentation, so I'm just going to stop it over here. And let me show you what I mean over here. So you can see that I have extracted a GIF from the simulation, and this shows the very oscillating nature of the flow in the wake region, which is very common in flow over a cylinder. So everybody who does CFD would know this problem. This is one of the basic projects that we do. So you can see how much post-processing data and information we can get from setting up a simple simulation in CFD. If you wanted pressure, density, any other values, you could extract that. So with that, I'll conclude the demonstration over here. So let's just summarize the key takeaways from this presentation. When to use CFD? Use it wherever. You can use it as a powerful design tool to simulate your flow and get all the variables, all the quantities that would help your product be better. The second thing is that Ansys Fluent in general covers a wide variety of physics, CFD applications. You can account for heat transfer, you can account for different phases. It's easy to set up. If you're interested in doing more complex simulations, definitely look at solvers like Ansys Fluent for your solution. And I'm sure Autodesk CFD also offers you a lot of options with the same regard. So yeah, with that, I conclude the presentation for today. Hopefully this was relevant to you and it gave you a very basic, very introductory idea of how to go about setting up your CFD simulations. And if you have any questions, I will take that now. So please feel free to leave them in the Q&A box.
Definitely, thanks for that. So let's go ahead and take a look at the Q&A. There are certainly a couple of questions we got on the YouTube side as well. So let's take a look. So a question, will you have another session for the content that was originally scheduled for today? Yes, so right now, since Nikhil is ill today and he had his presentation all squared away, we will reschedule that at some time in the future. I do not know exactly when that will happen right now, but keep on the lookout for that session on your calendars. And then a question here from Greg. Can you model a solid to gas in a reactor?
Yes. In Ansys Fluent, you can. I'm not so sure about Autodesk CFD, but you could model all sorts of reacting flows and combustion within Ansys Fluent. It's a little bit more complicated, but it's definitely doable within Ansys Fluent, and it is a tool that has been widely verified and validated in similar applications. So if you needed more information or some examples of doing combustion analysis using Ansys Fluent, feel free to reach out and I'll be happy to share some material with you.
Absolutely, and it's I think part of the reason, right, why we partnered with both Autodesk and Ansys. We just want to be able to provide our customers with the most robust solutions that are correct for their needs, right? So some people, they need just a general, fluid flow simulation where they can get away with using something like Autodesk CFD. And then we have people who have multi-physics and things along those lines where the complexity increases, exponentially sometimes. And in that case, right, maybe you want to go ahead and utilize some of the other tools we have, like CFD from Ansys with the Fluent application. So
absolutely. And because we're on that point, to anybody who's interested in knowing a little bit more about Ansys CFD software, we do have an Ansys AVA, just like the Autodesk AVA that KETIV hosts. Those AVA sessions take place every other Tuesday at 10 a.m. PST. And if you would like to, subscribe to those or look at some of those sessions, you could take a look at past sessions on the KETIV YouTube page. And if you wanted to attend any future sessions that focus on Ansys products, both for structures and CFD simulations, we can leave a link in the chat below and you could subscribe for those as well.
100%. So I'll let everybody another 30 seconds or so to ask any more questions that you do have. Like Snigdha said, there are some sign-up links for those webinars in the chat panel right now. So go ahead and click through those if you want to sign up. And without further ado, I think that's everything that we have. It looks like there was a question on YouTube about what Ansys module for modeling particulate flows specific to the food industry would be, the one to use. So when it comes to specific applications, please give us a ring, or shoot us an email, and we can take a look at that particular solution itself with you. I think that's probably the best, as opposed to kind of answering that here.
but just in general, there is something called the discrete phase model within Ansys Fluent, which can definitely be used to model particulate material for the food industry. So that's there as well. But yeah, if it's something specific related to an application industry, again, feel free to reach out and we can help you with that.
100%. All right. I think that's everything for questions. Snigdha, we really appreciate it. I'm sure the viewer base did as well.
Sure. Thank you so much, Nigel. Thank you.
Absolutely. Thanks, everybody. And we'll talk soon. Take it easy. Have a good weekend. Bye-bye.
Bye-bye.